Olá a todos, sejam bem-vindos a mais uma edição do Seminário de Física-Matemática. Hoje quem vai falar com a gente é o Renato Vasconcellos. Ele vai falar sobre The Weakly Interacting Tenfold Way.
Bem, primeiro agradecer pelo convite, é um prazer estar aqui falando com vocês. Só aviso, eu preparei essa apresentação em inglês, espero que não incomode ninguém. Bem, eu sou o Renato, eu sou um pós-doc lá na Unicamp. E eu vou apresentar esse trabalho que estou fazendo com o meu colega, o Lucas Musnik, lá do IMCC-USP. Então, vamos começar. What I'm going to talk today is a classification of fermionic system. So I'm going to start describing the Nambu space model for fermionic field operators. These are the basic objects that we're going to want to classify. And the idea of this classification scheme is that there are the irreducible symmetric fermionic systems can be classified into 10 classes depending on the types of symmetry they have. So I'm going to explain what does it mean for these fermionic systems to be symmetric and how they are classified by certain symmetric space of compact type. So I'm going to talk a little bit about this too. And the basic idea is that there are 10 types of these irreducible fermionic systems. So this is the basics of what I'm going to present. I want to talk about how this connects to a cohomology theory that's called complex and real topological K-theory. I'm originally an algebraic topologist, not a physicist. So actually, this is where I started studying these concepts in physics in order to understand better K-theory. So I'm going to go the other way today and talk a little bit about physics and say how this connects to these algebraic topological concepts. These cohomology theories are implemented into the study of crystalline fermionic systems. So basically how you can think of this as a study of how electrons behave in certain crystals and how this classification scheme can be used to classify stable ground states of these crystalline systems. I'm gonna, as an example, to illustrate how these ideas are actually used, I'm gonna talk about this particular model, the Sushi-Fricker-Higger model, which is the most simple model of what we call a topological insulator, which is a type of crystal that is an electric insulator in its interior, but its boundary is actually conducting. So it's a very interesting type of what we call a topological phase of matter. And in the end, I'm going to talk about what my research is, because this is how a few decades old results. And I'm going to talk about how this classification scheme is used to classify fermionic system where we assume the electrons don't interact with each other. That's what free means here. And what we are trying to do is to extend this classification scheme to take into account systems where the fermions can interact. So that's the basic idea of what I'm going to talk today. So I'm going to start with the physics of condensed matter physics, the study of basically fermions, or you can think of electrons in certain materials. And I'm going to talk about the Fock space model for many fermion states. I'm going to talk a little about creation and annihilation operators and how we use them to describe what these Nambu space models for fermionic field operators and what are the kinds of symmetries these kinds of systems can have. Important concept is the equivariant free Hamiltonians, the types of Hamiltonians these systems can have, and how we have space of dynamics associated to these Hamiltonians. And it's this space of dynamics that actually form the symmetric spaces that are used in the classification. So I'm going to talk about this. And finally, I'm going to end this part of the talk talking about the actual classification scheme. So just to start, in this context, we have Hilbert spaces of single fermion states. This is what we use to model this concept. And I'm going to be talking a lot about Sushi-Fricker-Higger model. So this is the basic Hilbert space for this model. We're trying to model a polyacetane wire, which is a crystal in the Z lattice, which is a periodic chain of C2H2 molecules with alternating single double bonds, and with n orbitals around each carbon. So the Hilbert space that models this is this tensor product of C2, Cn, and L2Z. So this is going to give us the wave functions in this model. Okay, so this Hilbert space models single fermions, and when we want to talk about many fermions, we actually use the Fock space, which is the exterior algebra. So we're going to be, these fermionic field operators are going to be operators on this Fock space. So just to start, in this Fock space, we have this vacuum state, which is the unit in this copy of C, which is in the 0 degree. For any vector in the state space, we have a creation operator described by this formula, which the basic idea is that given a state of n fermions, it adds another fermion in the beginning. That's the basic idea. And we have these annihilation operators that given a function, it annihilates one of the fermions in the system, being a certain number, and we take a weighted sum of this. This is the basic formula. So given an orthonormal basis for Hilbert space, we actually just some notation here. We use the cat notation for this basis space, and we associate a creation operator denoted by this AI dagger. And the dual elements are described by this brass with associated annihilation operators. And they satisfy these simple formulas. And one of the most important relations of these creation annihilation operators are the canonical anti-commutation relations, which basically means these creation operators anti-commute with each other, and the annihilation operators also anti-commute. And then you have a mix of creation and annihilation. If they are different, they anti-commute, but if they are the same, it actually ends up with a unit here. So I'm not going to get too much into this, but the basic idea is that these are the relations that allows us to do Fermi statistics on this Fock space. All right. So we get to the number space models of field operators. We're going to be fields of fermionic operators, and it's given by the direct sum of the state space and its dual. So we think of this as a space of both creation operators and annihilation operators. That's the basic idea. It comes naturally with a bilinear form, given by this simple formula. And this bilinear form actually captures the canonical anti-commutations relations. They always satisfy this relation. So the basic idea using this bilinear form, if you have a vector space in a bilinear form, you can create its Clifford algebra, given by the free tensor algebra quotient out by this relation here. And the idea is that these field operators are enclosed by multiplication, and this gives the free algebra generated by these operators inside the operator algebra of the Fock space. And the Hamiltonians of the system are going to live inside this Clifford algebra. This is a graded algebra, so each of the gradings is natural isomorphic to the exterior algebra over the number space. Just the multiplication is going to be twisted by this bilinear form. Okay, so for this system, we are interested in understanding its dynamics, so we have to talk about its Hamiltonians. And as I said in the beginning, we're going to start focusing on the free Hamiltonians, which are the Hamiltonians that model systems where the fermions don't interact with each other. Basically, it preserves particle number. And it's always given by this formula here, self-adjoint operators given by sums of this creation followed by annihilation operators. It can be captured in some basis by a self-adjoint matrix. Right. So first thing important about these Hamiltonians, that they act on the Clifford algebra by the adjoint operation given by the commutator. We can always represent in the given basis that we chose as a certain matrix that always has this form, and this is using some computations that are going to follow later. The important thing is these Hamiltonians generate a space of unitary time evolutions, which are unitaries of the Hilbert space, which given by conjugation by these exponentials. So actually, you actually have a dynamics on the whole Fock space, but since it's free and preserves particle numbers, the action on the Hilbert space induce the action on the whole Fock space. So we can focus only on this part. When you get to the interactions, that's going to change a little. So this is very simple. It's not a hard computation to see that this actually is going to be just a unitary group in dimension n. So things are going to get a little more complex when we add the symmetries of the system. So we need to talk about the symmetries of the system. So a symmetry is going to be basically a bijection of the number space to itself with certain restrictions. So there are a few types of symmetries. First, there are the types of symmetries that are unitary, which are the symmetries that are given by a linear operator compatible with both the unitary structure and the bilinear form. And we also have to consider the antilinear operators, the the anti-unitary operators that are antilinear, and also has compatibility conditions, except you have to do this complex conjugation because you have to deal with the antilinearity. So we have these two kinds of symmetries, and we divide these two kinds in further two kinds, so we get 4 kinds of symmetries. So the other restrictions we're going to have is compatibility with the decomposition of the number space. So we're going to consider non-mixing symmetries, the ones that send states, the Hilbert space to itself and the dual space to itself. So it sends like creation operators to creation operators and annihilation operators to annihilation operators. And the mixing are the ones that switches, sends the Hilbert space to its dual and vice versa. So I actually get 4 kinds of symmetries. We call a symmetry regular if it's both unitary and anti-unitary. So it preserves the Hilbert space and it's unitary. We have what we call a chiral symmetry, which is still unitary, but now it's mixing. And to do some physical considerations, we're not going to get into the details. We can always assume this kind of symmetries satisfy this condition that it squares to 1. We also have two kinds of antilinear symmetries. The first is named time reversal symmetry, which are the anti-unitary and non-mixing symmetries. And again, by this consideration, physical consideration, we can always assume the square to either plus or minus the identity. And the same thing for charge conjugation symmetry, which are anti-unitary and mixing, and they also square to plus or minus the identity. And these names come from some physical interpretation of the system of the symmetries. The time reversal and charge conjugation are rather self-explanatory, but I'm not going to get into the details of this physical interpretation. For now, we're just going to use this mathematical description of the symmetries. Okay, so I have these 4 types of symmetry, and we have to talk about what it means for a Hamiltonian to be compatible with the symmetries. For a regular symmetry, the conjugation of the symmetry with the Hamiltonian, it just means we have some unitary matrix that commutes with the Hamiltonian, with the matrix associated to the Hamiltonian, so it's simple. When you talk about the chiral symmetry, think that a little more complicated. The conjugation with the operator actually translates to anti-commutation with a certain matrix, which is, we can always find a basis such that this matrix that represents the symmetry is given in this form. For a time reversal symmetry, we also have compatibility condition given by conjugation with certain matrices. But now instead of anti-commuting, when you commute with these matrices, the Hamiltonian gains a complex conjugation. The form of this matrix T that represents the symmetry depends on whether the square is 1 or minus 1. And it can be given by one of these 2 forms. And for charge conjugation, we have something symmetry. It's kind of a mix of the previous 2 cases. When compatibility with this kind of symmetry means that there's some matrix C that when you conjugate the Hamiltonian, you get minus the complex conjugation. Okay? And again, due to antilinearity, the C, there's always some basis where this matrix C is given by one of these forms, depending on if the operator squares to 1 or minus 1. So this is a basic description of what kinds of symmetry we can see in this kind of systems. So going back to the Schrieffer-Higger model, the Hamiltonian of electron is described by this Hamiltonian. The first term basically is associated to the energy of an electron jumping from one cell to the next, from this bottom one to the top one. The second term, here's the shift operator that shifts from one cell to another. The second term just tells you the energy of an electron jumping from this top one in this cell to the bottom one of the cell to the left. And this is a term that tells you the likelihood of the electron shifting inside each cell. And this M is a mass term, which says how more likely it is for it to shift inside instead of jumping to the next cell. That's the basic idea of this Hamiltonian. And you can see that it has chimal symmetry. Given this operator here, we can actually compute that conjugation by it leads to a minus sign to the Hamiltonian.
Sorry, Renato, where is SH over there?
This is the shift operator.
Oh, shift. Okay.
This is shift. Just
here
means that we have an element here. It goes to the next cell because of the shift operator.
Okay.
And the matrix says that the electron here jumps through this. If there needs any clarification, please ask. So it's an easy computation that we can have chiral symmetry of the system here. Okay, so what we want to actually classify is the space of free equivariant Hamiltonians in irreducible systems. So irreducible here is going to mean that we are only considering the identity as the ordinary symmetry. And here we define the space of free equivariant Hamiltonians, which are the Hamiltonians, the free Hamiltonians that are compatible with all the symmetries we are assuming in the system. So for any choice of symmetries, we're going to get a different space here. And the idea of the classification of fermionic system is that what kinds of spaces can we get with this formulation. And the key here is that we can associate the unitary time evolution operators again, which is just going to be the time evolution restricted to the Hamiltonians that are compatible with the symmetries. And the classic observation in this line of study is that these spaces have a lot of structure. They are what we call symmetric space, which means they are Riemannian manifold with geodesic inversion at every point. This basically means that there are manifolds in each. Whenever we have a geodesic here, there's a symmetry to the minus point in inverting the direction of these geodesics. Being symmetric space means that all these local inversions can be extended to the whole space. And being of compact type just means that there's this notion of sectional curvature, and it's always positive. And the main observation of this classification system is that since the work of Cartan, like over a century ago, we understand the classification of this kind of spaces. And this is given here in this table. Basically, this table gives you the choices of types of symmetry we can have in our system in the presence of chiral, time reversal, and charge conjugation symmetries, and the choice whether the anti-unitary squares to 1 or minus 1. So if you do a little basic combinatoric, you see there are only 10 options here. Each of these 10 options, we can describe the matrix, in some basis, the matrices that represent the symmetries, and we can compute actually what are the Hamiltonians that are compatible with them. When we look at these Hamiltonians, we see the unitary time evolution spaces that we get are exactly the 10 classes of symmetric space of compact type that has been known since the work of Cartan. So this has been a work made by Palestrante and Zirnbauer, I think in the late 90s, early 2000s that they did this. And this tells us basically that the basic blocks of fermionic systems are given in these 10 kinds of types. Okay, so this has been known for a long time, and later there has been a lot of work trying to develop this and finding new ways of understanding this classification scheme. So what I'm going to talk now is about how this classification scheme connects to the algebraic topological notion of a cohomology theory. So I'm going to talk some algebraic topology now. So I'm going to explain basically what is a cohomology theory. I'm going to talk specifically about topological K-theory and construction using the Murray-von Neumann categories for projection matrices. I'm going to talk about spectra and Brown's representability theorem. The basic idea is that cohomology theories are represented by these objects called spectra, and the symmetric space that appear in the classification actually are spaces in the spectra that represent topological K-theory. So this is the connection between these two ideas. And so I'm going to show the reformulation of the classification in terms of K-theory. So this is the idea of this part of the talk. So a cohomology theory, what is it? It's a cohomology theory is basically a contravariate functor. So it takes a category of pointed topological space. And for each one, it sends to a graded abelian group. And contravariant just means that it swaps the direction of arrow. So if it has a map from X to Y spaces, the map from the abelian groups are going to go from the abelian group of Y to the abelian group of X. So if you took advanced calculus, you may think of like the Hahn cohomology. That's an example of cohomology theory. And they must be equipped with certain suspension isomorphisms and satisfying certain axioms of homotopy invariance. Basically, homotopical maps should give the same group homomorphisms. And exactness and additivity conditions, I'm not going to get into the details, but they're basically axioms that allow us to do computation with these kinds of objects. So there are many examples of cohomology theories. Some of the main ones are singular cohomology theory for some abelian group. I mentioned the Hahn cohomology. Actually, that's an example of a singular cohomology where the group G is the real numbers. This actually gives an example of this kind of cohomology. Another cohomology theory used a lot is cobordism theory, where we study spaces basically use some algebraic structure of the submanifolds of our space up to cobordisms between them. Just an example, I'm not going to get too much into this. And the main focus I want to give is the complex and real topological K-theories, where we study topological spaces based on some algebraic structures on the isomorphism classes of vector bundles over them. So, to get into some details about topological K-theory, how do I actually encode these vector bundles over these spaces? So we have this functor, a Murray von Neumann permutative category functor. It's a function that for any compact Hausdorff topological space, it gives a permutative category. This is just a category with some algebraic structure. The objects of this category are going to be matrices over the C-star algebra of continuous functions from X to F. F here is going to be either the real or complex numbers. So a projection matrix basically of these algebras basically encodes a vector bundle over space X. So the images of these projections are going to be the vector space in the fiber for each point X. And when you take them all together, this actually encodes a vector fiber bundle over the space X. So we want to talk about the isomorphism classes of vector bundles. So the morphisms in this category are going to be matrices U that give what we call a Murray von Neumann relations between these projection matrices. So this is a U that satisfies this. P is equal to U dagger U, and U dagger equals to Q. And this is basically a matrix that gives an isomorphism between the images of these projections. So this is a way to encode the notion of isomorphism between vector bundles. And as I said, this has an algebraic structure. Since we're constructing these as matrices, we can just take the direct sum of matrices. This has a neutral element, and this isn't exactly a symmetric operation, but this is symmetric up to isomorphism. That's what I mean by a permutative category. We have an explicit description of these isomorphisms that swaps two projections. Okay, so building this category then encodes these vector fiber bundles. We can define the functors, the actual contravariant functors that give us the cohomology theory. The construction basically starts by taking this K00 group, which when you take this just means that we're taking isomorphism classes of this category. This structure actually gives it a structure of a commutative monoid, not a group. It's lacking the inverse elements. So basically what we do here is we make the same construct, we call the coding construction, which is the same thing that we do to build the integers from the natural numbers. We formally add inverses using the difference of pairs. So we use basically the same idea here to transform this commutative monoid into an abelian group. From here, given a pointed space, we actually build the K0 functor. Is going to be the first degree group of the cohomology theory as the kernel of the map induced by the inclusion of the base point. The basic idea here is that for any space, we are going to always have trivial bundles over them. So this doesn't give you a lot of information about the space. So you basically them out because they are not telling you anything about the space. And we need those suspension isomorphisms. And in order to get them, we just define the higher dimensional groups of the space, the K0 groups of their suspension. So this is the basic idea of the construction, very express. The important thing here is what's going to connect with the physics part of the talk is the notion of spectra and how they represent cohomology theories. So a spectra is a basic object in algebraic topology. They are given by a sequence of pointed topological spaces and suspension weak equivalences, which are just maps from one space in the sequence to the loop space of the next. And this very important theorem by Brown says that any cohomology theory you can think of is actually represented by a spectrum. And when I say represented, I just mean that the abelian groups of the cohomology theory are given by stable homotopy groups of the mapping spectra from your space to your spectra, which are given by this formula, such a co-limit of the homotopy groups of these mapping spaces here. And this co-limit is taken under this suspension weak equivalences, basically. The spectra that represents singular cohomology is well known. It's given by a certain tensor product. I'm not going to talk a lot here. This is just examples. It's not going to be super important for us. But the main thing is that the topological K-theory, cohomology theory that I talked earlier, are represented by spectra that are known as Ku and Ko. And we actually have already seen them in the table earlier. So the basic thing to observe is the following. When we take the colimits, when we assume these Hilbert spaces have infinite dimension, each of the symmetry structure, for each of the symmetry structures, there is a symmetric space of compact type. That is the classification of another symmetric space of compact type. Basically, we get a natural suspension map between them. And we can see that these classification spaces are already spaces that appear in the first column here. They're just shifted. And you actually can group them in two, because these two, just the classification of UN is this one, and the classification of this one is just UN. So you can build a spectrum that just cycles through these two spaces repeatedly. These 8 form another group of 8, and we can build a spectrum composed of 8 spaces that just repeat itself after the 8. The 9th space is going to be the same as this first one here. And this has a spectrum structure, and this spectrum is the spectrum that represents topological K-theory. The first one is the complex K-theory, and the next one is, is the real K-theory. And here we get some of the stable groups of the points, which are going to be the basic building blocks of this cohomology theory, basically. And this is going to be used to compute the classification of ground states of the crystalline fermionic systems. So I'm going to talk a little bit about this, how this view of the classification of fermionic systems using topological K-theory is actually used to understand the stable ground states of crystalline fermionic system. So I'm going to need to talk about some crystals and energy, and this can sound like very quantum coachy, quantum healing, but it's not. It's just physics and the study of crystallographic groups and what are crystalline fermionic systems. So we have to talk about the crystallographic groups, which are the kinds of groups that describe the symmetry of crystals, basically. And with this description of crystalline system, we can actually use them to classify the stable ground states of these kinds of systems. So what is a crystallographic group? It's a discrete group of the isometries of Rd. And it's crystallographic. It has a normal subgroup of translations, N, which is a lattice. Lattice just means that it spans the whole space. Such that the quotient space is a subgroup of the orthogonal group. This is what we call a point group. It's going to be the group of symmetries that fix one of the points of the symmetry. A basic example is you can think of ZD inside of RD, and we get this semi-direct product of groups that gives the symmetries of this lattice inside of RD. Important notion that we're going to need is the notion of the momentum space associated with the systems. That's also called the Brillouin zone, which is the Pontryagin dual of the lattice. Basically, the group of homomorphisms from the lattice to the circle. In this example of lattices on the ZD, the Brillouin zone is going to be isomorphic to the torus. When I talk about crystalline fermionic systems, basically we take many copies of these irreducible systems that we talked earlier, and we distribute them over the lattice of a crystallographic group. So this is how. So the Schrieffer-Higger model is going to be an example. All those cells represent some irreducible system, and we are distributing them over the integers. So it's an example of D equals 1. Okay. As said, we are interested in this system of understanding the stable ground states with the states of minimal energy of these systems. And there's a result. I'm not going to get too much into the details, but the idea that these stable ground states are actually given by the K-theory, equivariant K-theories of the Brillouin zones of the crystallographic systems. So when there are no anti-unitary elements, so there's either just the regular symmetries or the chiral symmetry, it's given by complex topological K-theory. And when in the presence of anti-unitary operators, we have to use real topological K-theory. And this J term is dependent on the kind of symmetry, just like in the table before. So depending on the symmetry, this dictates what this J is going to be. So an example of computation, in this simple case of a system in the lattice given by ZD, we want to, in order to understand the stable ground states, we have to compute the K groups of the torus. Because the torus is just a product of circles, it actually can describe as a certain sum of the K groups of spheres. You can do this computation. And since we have to take into consideration equivariance with the point group, we actually have to consider irreducible representations of these point groups to get an addition of many copies of these K groups of the spheres. With this formula, Kornfeld and Carmelli actually computed all the possible stable ground states of crystallographic systems in this ZD lattice. There are crystallographic groups that are in other kinds of lattice, and their work didn't address that. I'm not sure if someone addressed the other groups. I'm not exactly sure. But this is just part of the table that they did. Each column is one of the possible crystallographic groups, depending on what point symmetries you allow for the system. And for each of the symmetry classes, you can actually tell what is the group that represents these stable ground states. So this is very nice. And they mention in this paper that this can be done by a computer algebra program, to just giving the information, they spit out all these groups. And this is used in order to understand better, to predict what kinds of crystal can have topological phases of matter, such as the topological insulators that I talked before. So what I want to talk a little bit more is the details about the Sushru-Vickers-Higger model and how all this K-theory actually can inform us about the behavior of this material and why it makes it a topological insulator. So I'm going to talk about how in this system we actually can use the Fourier transform to reduce it to irreducible cases. I'm going to talk about the important notion of the gap in the energy spectrum. This is going to be important later also in order to define what it means for interactions to be weak. It's going to be important through the work I'm doing. I'm going to talk about fermionic operators and boundary electron ground states, which are certain notions connected to the topological K-theory of this system. And finally, I'm going to talk about the bulk boundary correspondence, which is a theorem that is proved using K-theory. It's basically the property of this model that tells us that it's going to be a topological insulator. Basically, there's an invariant of the bulk given by the fermionic operator, and it has a relation with this boundary electron ground states. And this relation tells us there are going to be electron ground states in the boundary, which are actually conducting. So here's how the actual physical phenomena appear from this classification scheme. So what's the idea? Okay, so we want to reduce our crystallographic system into the reducible cases. We use the discrete Fourier transform, that is an isomorphism between L2Z to the L2 of the circle. This transforms the Hilbert space of the Sushru-Vickers model into this Hilbert space, which is the space of sections from the circle to the trivial bundle, whose fibers are going to be copies of C2 tensor proctor Cn, so it's isomorphic to C2n. To see the connection with the table here, you can see that when we actually apply the Fourier transform to the Hamiltonian of the system, we actually get in each Z in the circle a Hamiltonian of this form, which is closer to the Hamiltonian expected from the classification scheme. Okay, so this is the start of the computation. First observation is that in each Z in the circle, in the momentum space, we get a certain energy. So we get a function from the point in the Birley zone to a certain energy given by this formula. And we always get a positive and a negative energy here. Important observation here that we have a gap here that's always given by 1 minus m. M is that mass term that tells us how likely it is for it to switch inside each of the cells. An important observation that H is gapped if m is different from minus or minus 1. So there's going to be this gap in the energy. In that case, this m is different from the possibility of switching cells. Okay, so we're going to assume that our Hamiltonians are gapped. In this case, you can define the Fermi projection, which is the projection into the eigenvectors whose energy are below 0, so the negative energy. So, which is how we encode the electron ground states of the system with this projection into the negative energy elements. We need to associate what we call the flat band Hamiltonian. Basically, we associate to this Hamiltonian the Hamiltonian which sends eigenvectors to itself if they have positive energy, and to minus itself if they have a negative energy. That's the description of this associated Hamiltonian. It can always be described by a matrix by this form, where UF is a unitary operator. We call the Fermi unitary operator. And we can derive the existence of this unitary using the fact that this flatbed Hamiltonian still has chiral symmetry and squares to 1. This is the computation we can make to find that we should have some unitary of this form. These two operators, the Fermi unitary operator and the Fermi projection, actually store the same information. You can derive one from the other, so they can represent the electron ground states of your system. Okay, so we want to actually use this notion to actually get this number, because we have the Sushil-Ficker-Higger model is a one-dimensional system. So here from the table, we expect to associate such a number to it, which is going to be the bulk invariant of the system. So how do we get this integer, actually? So when we take the Fourier transform of this flat-band Hamiltonian, we actually get a Hamiltonian in this form. And the bulk invariant is going to be the first Chern number of this Fermi unitary operator. And this is basically a type of winding number. So unitaries are their determinants are going to be an element of the circle, a complex number of absolute value 1. So if we take the determinant for each one of the elements of the circle, we actually get a map from the circle to the circle. And whenever we get a map from the circle to the circle, we have the notion of how many times this map is winding around the circle. We actually can compute this winding number directly from the description of the UZ here, the transformed Fermi unitary operator. And we actually, doing the computation, we see that the value depends on whether m is between -1 and 1. And in this case, you actually get the minus n. And in the case when m is greater, you actually get 0 here. This map is not going to be surjective, so it's going to be trivial. So we actually have this non-trivial behavior of the electron ground states only if this m is small enough, basically the idea. Okay, so we want to associate this. This is going to be the bulk invariant, and we're going to want to talk a little about how we can derive the fact that they're going to be conducting boundary states. So how does these boundary states appear? So the boundary is going to be the boundary of the half space associated to the system. So we take the Hilbert space associated, that's described similarly, except we get the L to N. So we're throwing away all the negative element cells. So the boundary is going to be this cell here, which is associated to the number 0. And we have a boundary condition given by this Dirichlet boundary condition, which is just basically the description of the Hamiltonian, but applied to this half space. It's going to be a big difference, basically because the shift operator here acts very differently, because now the shift to the left is actually going to delete some information because there is no cell here in order for the electron to jump. And actually this makes this new Hamiltonian have a non-trivial kernel, so there are going to be 0 energy elements here. Important observation here is that this new Dirichlet Hamiltonians also have a chiral symmetry, which is going to be important in the derivation of the description of these boundary states. So how do we derive these boundary states? We want to look at the span of the eigenvectors for energies that are very close to 0. So it's not just the 0, but just in the neighborhood of 0 energy. Important observation is that this space is invariant under chiral symmetry, basically because when you apply it, you have this anti-commutation with H, so up here this minus sign. So we're going to have this symmetry in this this space E. This means that as the chiral symmetry operator can be diagonalized, and this diagonalization actually tells us there is an orthogonal decomposition of this space E into the positive energy elements and the negative elements, negative energy vectors. Okay, so again, we can talk about the spectral projection, which are the projection onto the eigenvectors of energy below this delta threshold here. And this always can be decomposed into the projection into the positive part and the projection into the negative part. And when we apply the chiral symmetry to this operator, what it does is basically it multiplies the negative energy vectors by -1, and it just fixes the positive energies here. So using this observation, we actually can describe the boundary invariant of the system. It's going to be the zeroth Chern number, which is basically the difference in dimensional between the positive energy, we also call it positive chirality elements, and the negative energy elements here. And the bulk boundary correspondence, which is our result, uses operator K-theory, so I'm not going to get into the details of how we prove, but we can prove that the minus the first Chern number actually equals this zeroth Chern number. So there's this invariant associated to the bulk of the electrons inside the system. And what this is telling us is that because it is for m small enough, this is going to be n. This guarantees the fact that this difference in dimensions is going to be n. So this gives n elements in this positive eigenvalues space. And these are going to be the conductive electrons in our system. So this is how this K-theory considerations actually can tell us about the behavior of these boundary states. Okay, so this is very well-known results to understand how this classification is used to understand the stable ground states of crystals. And what we are trying to do in our research is try to expand a little more the application of this classification scheme. This has been expanded in some cases, with some disordered Hamiltonians. What we want to include that's not in the literature yet is what happens when we allow the electrons to interact with each other. And if you allow any interaction, the behavior of the system changes dramatically. So it's not expected for the classification to still work if you allow any kind of interaction. But if you allow it to be weak enough, we expect it to still satisfy the same kind of classification scheme. So the idea is that we can use this greater class of systems in order to describe new spectra, which we expect to be able to deform to the KU-KO spectra. And this deformation is what basically going to encode the idea that the two classification schemes work basically the same. That's the idea. So just giving a little details about the idea of what we are doing, we need to consider systems with interaction between the fermions. So Hamiltonians of interactive fermionic systems live inside this even Clifford subalgebra. The three Hamiltonians lived in the Clifford algebra of degree 2. But when we consider actually interaction between them, we actually have to consider operators with even degrees in this Clifford algebra. We want to talk about weakly interacting, and what we mean by weakly interacting is associated with the gap that we saw in the Sushir-Higger model. So basically we have the Fermi level of the system, of the Hamiltonian, and we say that it's gapped if there is a non-zero closed interval around this Fermi level, which doesn't intersect with the spectrum, just like in the graph that I showed a few slides before. So whenever you have an interacting Hamiltonian, we can always decompose it into the part that is free, which is a type of Hamiltonian that we saw in the original classification. And we can add a certain term from this even Clifford algebra. And we say that this Hamiltonian is weakly interacting if this lambda term is small enough so that H0's gap doesn't close. So this gives a precise definition of what it means for the interaction to be weak. So we actually get a class of Hamiltonians, and we want to classify the spaces of weakly interacting Hamiltonians. So we have an explicit description. They're going to be these self-adjoint operators in this even Clifford algebra, which are going to have to be compatible with certain symmetries of the system that are described in the same way. This part doesn't have to change anything. And we just have to add the assumption of them being gapped. Now, they again generate space of unitary time evolution, again by conjugation of the exponential of I times the Hamiltonian. Here some complications appear because this unitary lives in the C-star algebra that is the completion of the Clifford algebra. And we can't really think of them as operated on the Fock space anymore. We have to take a K and S construction, a new Hilbert space. But we can still talk about them as unitary operators inside the C-star algebra. So we still expect to be able to form a space here that should be able to deform into a space that is isomorphic to the time evolution operators of the free cases. So the idea of what we are trying to prove is, can we still equip this sequence of spaces with spectral structure? Basically, we expect to be able to have maps to loop spaces of other symmetrics in the same fashion as in the classical classification of free fermionic systems. Given this structure, since we have spectra, we should be able to use this description to see if we can build a homotopy between these larger spaces into a smaller space that are isomorphic to the KU and KO. So if we have to do spectra that are homotopy to each other, they should represent the same cohomology theory. So basically the interpretation is that the classification schemes should still work equally, just the computations have to be done in this larger class of operators. Well, this is what I have to say. So if anyone has any questions or comments, and thank you for coming here.
Are there any questions or comments?
At the slide number 9, when you talked about the symmetries and
Which slides?
I was wondering if there are any kind of parity symmetry within this
Parity
scheme.
symmetry.
It's inside? The same thing. Okay.
Okay.
So I was just...
I'm not familiar with the term. Again, as I said, I'm an algebraic topologist, so some of the physical terms I still haven't internalized.
Now it's better.
The chiral symmetry, basically what it does, it tells you that the space can be divided into like this positive part and this negative part.
Exactly what I was thinking.
Because if you see here in the table, whenever you have this, you always have this type, and it always the diagonal, and this sort of captures on these two separate and positive and negative parts.
Okay. Thank you very much.
Thank you, Renato. So I have, I guess, some questions. So I didn't quite understand the whole of the role of the dimension of the lattice, because the Schreiber-Heger model that you defined was defined on the line.
Yeah.
But then you showed us some classification tables of some systems defined on Z3, for instance.
Yeah.
So why do you need to restrict your analysis to only on the line instead of ZD?
Oh, you don't have to restrict actually. This is just the simplest model of the topological isolator. There's actually examples of it in 2 dimensions, in 3 dimensions. This is just the simplest to actually describe the ideas that goes into it, but this analysis can be done in higher dimensions. Basically, what is going to change when you have higher dimensions is like in this half space, instead of like Zn is going to be n times Zd, so it's going to have something like, in 2 dimensions, it's going to be something like this. This continues in this direction. And there's going to be a boundary here.
Oh, this boundary. Okay.
And the basic idea of everything that happens here in the Sushil-Freer model still carries on to the higher dimensions.
Okay.
Part of the difficulty may come because the higher the dimension, the more symmetries you can have of the point group. And then by the... so this... here. So when you have more point group symmetries. This can add more terms to the classification of stable ground states. So this can make the computations a little more tricky, but the basic idea is the same.
Okay, and about that, there is some phenomena, like, this is like a Lego question. I don't know how to say Lego in English. So usually in like spin systems, you see some kind of phenomena when you go to higher dimensions. Some aspects like critical exponents like stabilize, like they at some point start to be equal. Do you see some phenomena like that when you go to higher D? Like if D is larger than something, then the theory gets trivial and everything.
I think that stability phenomena here, because there are two dimensions that are relevant. There's the dimension D of the actual crystal, but there's also a dimension N of how many orbitals you're considering here. And when we talk about the stable ground state, the stable means that we are considering the limit where we're considering infinite number of orbitals in each cell. So actually this only works if you allow this number of orbitals to go to infinity. Because otherwise you don't actually add a group, because you always can stack orbitals up on each other, but the notion of subtraction only appears in the stable limit. So this actually occurs, but it's not associated to the dimensionality of the crystal. It's associated to the number of orbitals.
So, and another question, you talked about weakly interacting systems, but you still are studying the ground states, Yeah, so what about if you try to study systems with a positive temperature? Like even positive temperature, but it's small, let's say.
That's a good question that I'm trying to understand better. I don't have a good answer for you right now, but I know that's something we have to consider. Because I'm working with Lucas Musnik. He was a physicist. He's becoming a applied mathematician. He's working with Pedra in CMC. And one of the questions we want to use this for is eventually working out this actual classification. What we want to understand are questions like, okay, what is the critical temperature in which a certain crystal continues being a topological insulator or not? So this is kind of thing we have to understand better, but at the moment I don't know exactly how this is going to go. But it's something that we're going to consider down the line. But don't have an answer right now.
And now another question that it's more speculative also. You talked about fermionic systems, but there are also bosonic systems. There are some kind of classifications in this sense for this kind of
all the papers I read mention that there are regular considerations of bosonic systems too. Basically, you're going to have to exchange the Fock space to a symmetric space to consider the bosons. But I've never seen such a neat classification of the bosonics. Every paper I read that mentions it is usually like an appendix. But from what I understand, there's not such a neat classification that is for fermionic case. But I'll give the caveat that I'm not super well read on that part, so maybe someone knows it and I just didn't get there. But if it exists, it seems to me that it's just going to be more complicated in the fermionic case,
So thank you. Let us thank Renato again.
Thank you for inviting me. Obrigado. Tirar a pena. Você pode me mandar os seus slides por e-mail? Posso, sim. O que vai acontecer vai ser o seguinte, eu vou colocar você no site e depois eu te aviso. Ok, beleza. Eu nem falei nada porque era uma besteira, mas eu acho que você escreveu o IMEC errado no site. Você tá brincando? Faltou o E. Você escreveu IMCC. Não.